This podcast is for general informational, educational purposes only and is not to be considered medical advice for any particular patient. Clinicians must rely on their own informed clinical judgments when making recommendations for their patients.
Welcome, everybody, to PHM from Pittsburgh. This is now our 23rd episode. Should be our 23rd episode when you're listening to this. I am still your host, Dr. Tony Tarchichi. I'm a med-peds trained pediatric hospitalist here at UPMC Children's Hospital of Pittsburgh. We have been doing this since October 2016, and this episode today is interesting. I'm going to set the stage for why we're talking about what we're talking about. Early April, I was at a conference. As some of you know, I'm the fellowship director for the UPMC Children's Hospital of Pittsburgh Pediatric Hospital Medicine Fellowship. And Cincinnati was kind enough to put together a very nice conference on research techniques and how we teach research to our fellows, and just a really nice collaborative exchange of ideas with some talks by some very good speakers and great workshops. And it's put together by, the big names like Samir Shah, Neha Shah, Joanna Thompson, Karen Girardi. So thank you all. They put together a very nice conference, and they were very nice hosts. But when we were there, my current guest, who I'm about to introduce, brought up a topic about the future of research. And this is an area I don't know very much about in terms of where research is going and new research techniques. So let me introduce my guest, and we'll talk about what he said, because I find it fascinating and make you, if you're interested, I hope you will. So Dr. Matt Hall. Matt is the principal Bio-statistician at Children's Hospital Association, CHA, and the director of the Children's Hospital Institute for Pediatric Research, CHIPR. He has extensive expertise not only regarding statistical methodologies, but also in the conduct of pediatric research using large data sets containing detailed hospitalization data. He provides statistical support to all divisions of CHA, Children's Hospital Association, with a particular focus on performance improvement. He oversees the research and statistics team at CHA, and his responsibilities include the analysis of CHA's Pediatric Health Information System, PHIS, to provide owner hospitals with prescriptive analytics and to determine ways in which data can be used to improve children's health care. In this capacity, he leads multiple collaborative research groups comprising of over 100 physician investigators from children's hospitals in order to perform a variety of epidemiologic health services and policy research projects. He is on the editorial board of Hospital Pediatrics and has published over 250 papers, many of these using data mining techniques. So I want to first welcome Dr. Matt Hall. Matt, welcome to the podcast. Thank you for joining us today.
Thank you, Tony, for having me. It's my pleasure to be with you today to talk about machine learning and how we can use it for research purposes.
Now, before we go any further, there is CME associated with this podcast, courtesy of the University of Pittsburgh. So thank you, University of Pittsburgh. So we do have to do our conflict of interest statements. I will start. I have nothing to disclose.
I have nothing to disclose either.
Wonderful. So, Matt, do you remember what you said at the conference that piqued my interest?
Well, Tony, I think the conversation was around what types of analytics should be taught to PHM fellows. And the conversation revolved around very traditional statistical models and methodologies. And my comment was that we need to be preparing researchers and fellows for the future by teaching more contemporary modeling techniques, and mainly the machine learning techniques that are becoming more and more common in research, and some of the artificial intelligence that's being done within pediatrics as well.
Now, when I hear machine learning, my mind goes right to IBM's Watson, and when they beat I forget his name on Jeopardy, and how that's being used for everything. Is that the kind of artificial intelligence you're talking about?
It sure is. That would be one application of the type of machine learning I'm talking about. There's a lot of different techniques out there. Machine learning is a fairly broad umbrella of different analytic techniques that are grouped together, and we can talk about the commonalities of them, but that would definitely be one of the applications that most folks are familiar with in machine learning.
So for those of us who aren't as familiar, short of that Jeopardy challenge and the commercials we see where Watson's used for everything from basketball to ordering supplies in Brazil. Can you give us an idea, what is machine learning? How are we going to use it for research, kind of a background for those of us who don't know?
Yeah, sure. So machine learning, as I mentioned, is a very broad umbrella of a lot of different analytic techniques. So they all share common features, though, in that they're trying to understand complex relationships from your data. So this is typical to what you do as a clinician. You try to tease out different relationships from different features of your patients to come up with different diagnoses or different treatments, or potentially even predict what an outcome may be for a specific patient. And so that's typically what machine learning is that we're trying to train a computer to think like a human and to learn like a human so that they can make appropriate predictions of potential future events.
Can you give me an example of research that would use machine learning that would be really pertinent for a hospitalist?
Sure. So we've seen, that the machine learning has really taken off within the last 10, 15 years in research, and particularly in pediatric research. And we've seen it in a number of different journal articles that may be useful for your audience. One of the more recent publications that I've seen in pediatrics was to determine at the time of an ED triage whether or not a child would need to be hospitalized for asthma. And so they collected a number of different features or variables at the time of the triage and used that in a machine learning algorithm to determine or predict whether or not a child would need to be hospitalized for their asthma exacerbation.
So it's taking all of the data in our EMR systems and analyzing it, I'm assuming faster and using more data than humans can do to make these predictive models. Is that relatively accurate?
That's exactly right. So you can build up these models, and let's just kind of stick with our example here of predicting the likelihood of an admission for a child at triage. You can build up these models, and then once you have them built, you can implement them into your EHR so that when a new child comes to the ED, their information can be fed into the model to give you a prediction of whether or not this child will need to be admitted or not. One of the nice features about these machine learning techniques is that they learn. And so you can also not only build the model and put it into place in your EHR, but the model can continue to learn from the data that comes through. So every time a child comes in, it will predict whether or not the child will need to be hospitalized, and then you can observe whether or not that child actually needed to be hospitalized or not, and that information can be fed back into the algorithm to improve its performance in the future. So it's constantly learning. It's not stagnant like a lot of the historic statistical models are. You build them, you place them into an application, and then they don't learn or continue to improve off of new data. They're somewhat stagnant in that sense. The machine learning, one of the nice features, as I mentioned, is that they learn from new data. So it may, have predicted that a certain child is going to need to be hospitalized, but they're not hospitalized. So it will learn from that error in prediction that it made for future cases that come through. So the algorithm itself continues to improve as new data flows in.
So this sounds like it would have to be very regional because, certain hospitals practice certain ways and there's variations even from physician to physician, but certainly from hospital to hospital, even in terms of what diagnosis codes they use, whether it's status asthmaticus or the asthma exacerbation, or is the machine learning system able to overcome all of that and it's used nationally?
Well, I'd say that there are folks that are working in this space that are trying to create more national applications that can be implemented regionally or locally and then the model itself can learn from the data locally. But for the most part, I would say you're right, Tony, in that the applications that we see used in children's hospitals currently are very localized to that setting. So, if they're trying to predict readmissions or something along that line, they may start with a base model that has been developed in their system or maybe more nationally. But then the learning system continues to improve from that local setting. And so I'd say, yeah, for the most part, you're right, is that they do need to be localized in a sense, but there are some common features probably that you can elucidate from national data that could be helpful for a local instance of a machine learning algorithm implementation.
So now you can use these models to predict whether someone should be admitted or is likely to be admitted, and then whether or not they're likely to be readmitted. If they're already admitted, let's say for asthma, and you want to discharge them, the model in real time can say, if you discharge this patient now, there's a 50% chance they'll be readmitted within 7 days. Is that accurate?
That's exactly right. That's how we've seen this used in hospital applications currently. Would be for predicting the likelihood of a child coming back if you discharge them at this time.
Now, I'm going to ask you a paranoid question, Matt. We keep hearing about as the machines are taking over our jobs. It's on TV. But it sounds like this does take some of the medicine out of medicine, meaning if I'm not being asked to decide whether a patient should be discharged or not. Now, granted, we've been inaccurate. If you look at the numbers, statistically and historically, we're inaccurate. People come back. That's one of the whole purposes of QI as a field in general, is our inaccuracy in discharging and predicting when someone's ready to go and other things. But this does sound like it's really going to take a lot of the work out of my hands. Am I being too paranoid?
Well, yeah, I think in a sense that this information can be useful to the clinician for decision-making purposes. I don't think that will likely, at least not in our lifetimes, get to the point where the machines actually make decisions for you clinically. But I do think that the utility of these machine learning algorithms is to process a large amount of data and reduce your cognitive load almost. And so currently, let's just say you're dealing with a medically complex child who comes in, they're on 30 different medications, they have a trach, they have a ventilator. It's a huge cognitive load for the clinician to think through all of these inputs and make clinical decisions. That's, I think, where the machine learning techniques can come in to provide some guidance to you. So it's not ultimately going to make the decision for you, but it is going to help you think about what's the likelihood of certain types of events happening, what are the potential diagnoses for this child or the alternatives in the treatments that you could take and things of that nature, and then the ultimate prognosis. So I think it's likely to be more of a useful tool and guide for the clinician rather than replacing the need for a clinician to think critically about a specific patient.
Now, help me understand how, I'm not a computer programmer at all. I'm going to start with that. But when you're programming or when you're starting this up or when you're deciding you have an AI system and you want to look at X, Y, or Z, do you feed them or have them look through all of the literature in that particular area, and then they analyze it and catalog it and then look at your local EMR data? Or do you just have them look at your EMR data, feeding them what you're interested in? You understand my question, I guess? I hope that's okay.
Yeah, for sure. I think it depends on the application and who's doing the research and why they're doing the research. It's most common that hospitals will use a wide variety of data points, let's say, out of their EHR to make predictions. And so they'll feed these algorithms a massive amount of data on a ton of different lab tests, on imaging, on all the clinical characteristics of the child. A ton of data will be passed into the model, and the machine learning will look for features within the data that are helpful for predicting the future. So most of these models will take historic data from your EHR where you know the outcome for that child, and let's say you're just predicting readmissions. You know all of their labs, you know all of their clinical conditions, you know a ton of data on this child, and you know whether or not they came back and were readmitted within 7 days to the hospital. Well, you'll use all of that retrospective data to train your model. And so you'll feed it all into the algorithm, and the algorithm will identify some of the relationships that are useful in the data for predicting whether or not the child will come back to the hospital. And then you can assess the validity of that model using future data. So a new child comes in, all right, we've built our model or machine. We can put their data through the machine and predict whether or not they'll come back, and then observe whether they came back or not. And so we can assess how valid our model is that we've created prospectively. Okay, so we develop it retrospectively and then put it into place and then observe what happens prospectively to see how valid our model is.
So one of the patients you brought up was like our neurodevastated patients with multiple issues who present. There is not a lot of data in the literature on those patients in general. There's more being published, and I know there's more research being done. Places like Cincinnati are doing a significant amount. But I guess my question is, for those patients, there's so much variability in practice. People, for each admission, may put all of the problems in the problem list or just a couple. I would assume a patient that complicated with that many issues and that variability in practice, the machine learning, the AI learning would take longer to get it right, but could eventually get it right. So in a patient like that where we don't have a whole lot of data, we could theoretically get a bunch of data within a relatively short period of time using this. Is that right?
That's right, Tony. So even these rare instances of diseases, over time you could build these models without having a large data set to start from. And so, as I mentioned earlier, one of the key features of machine learning is their ability to learn. And so even if you don't have a robust set of data to build your initial model on, as additional children come in with these types of conditions, the machine learning model can improve and get better and better over time. You know, it's not that different from you as a clinician, right? I mean, you see your first medically complex child, it's very difficult for you to think, about predicting what may happen with this child in the future. But the more and the more you see medically complex children, you start to learn patterns in these children. You start to see, that kids with certain types of technology may respond somewhat similarly to different types of treatments and things of that nature. So again, the machine learning is trying to mimic the human learning, and the more experience a human has with a type of child, the more accurate their predictions will be of what that outcome will be for that child. And so the machine learning is similar, right? The more inputs it has over time, the better and better it will become.
I guess where I'm stuck, I understand what you're saying. I guess where I'm stuck with these, specifically these complex patients, is what we're, this may just be my ignorance on computer programming and how these EMRs work, is what I see as a hospitalist is, for instance, a patient comes in, they have 20 problems, but they're here for respiratory distress pseudoviral URI. And sometimes that's the only diagnosis codes that are there, respiratory distress viral URI. And I guess maybe the AI is able to look through the history of that chart and find the other medical problems the patient has had and pull them in. And this is just how little I know about AI, how EMR and AI work and interface. Whereas my question kind of is, how will it be able to tell what all the other problems are if I, as a clinician, am not putting them in the problem list with each encounter? which sometimes I don't. You know, if the patient has panhypopituitarism, I may forget to put that one in one time. You know, that just happens. So I'm assuming that there's a way the AI can pull all that out.
Yeah, so it's a good question, and I think maybe you're talking more about the data, the underlying data structure and the robustness of the data that's there and available for the machine to learn from. And I think you're right. I mean, I think it's the more robust data you have underlying this, the more accurate the predictions will be. And so in the ideal state, the machine will have access to all the data for this patient, not just for the current hospitalization for this child, but we'll have all the historic information. You know, if you have the clinic data for that child, that would be available to the machine. You would have, different lab results from outpatient clinics and things of that nature available to the machine to learn from. So all of that data from the historic encounters for that patient ideally should be available to the machine to make its prediction. If all you have on this child is what's available on the current hospitalization, it's going to be significantly, missing a lot of data, and it's going to create very inaccurate estimates of what the future events could be for this child. So the more robust data you have for the child, the more accurate the prediction will be. So you're right. I mean, it's like even if you don't code the fact that the child has cerebral palsy on their current admission for a UTI, the algorithm should have at its disposal the fact that this child has cerebral palsy based on prior encounters with this child.
It almost sounds like if somebody is fresh, finishing medical school, going in the pediatric residency, knows they want to be a hospitalist, it may not be a bad idea to get a computer programming degree of some type. Is that what you would use to put in these algorithms, or is it another type of... That's how little I know about this, Matt. So what type of a background do you have to write these algorithms to help with these AI?
So a lot of these tools that have been developed are somewhat push button, right? So you don't need to know fundamentally how these things work in order for you to create a machine learning tool, all right? So there's software out there that is available that will implement these techniques just like in statistics. So you may not know how to build a logistic regression model, but there is software out there that will help you build a logistic regression model. Same is true for these machine learning techniques. There's, a bunch of computer programmers out there that have developed software that will create these machine learning models for you. So you have to provide it with the inputs and identify what the output is or what you're trying to predict is, and the algorithm itself can run to build the model for you. And so it's not that different from statistics in that there's software that's developed already that can implement most of these machine learning types of techniques. So I wouldn't say necessarily that new fellows or folks that are going into research in the future need to understand computer programming so that they can program how these models are built. That's already being done and has been done by computer scientists and by statisticians. It's more of how do you leverage these tools, and then how do you interpret them, Tony? I think that's more important. And I'd say the same thing for statistics, more common, traditional statistics. You don't need to necessarily know how to build a generalized linear mixed effects model, but you do need to know why you would use those things and what the interpretation of the output of those things looks like and what it means. And so by focusing on mechanics of how they're done, more on the interpretation of what they're telling you, I think is more important for our fellows right now.
So do you see this as becoming one of the primary research methodologies in the future, and this is where most research is going to use, or do you see this as just one part?
I think, I'm kind of a conservative optimist on the machine learning. There's been a lot of promises from machine learning that haven't really panned out. So I'm a bit of a conservative optimist on this. I think that folks are going to continue to use these techniques into the future in an ever-increasing amount, but I don't think they'll necessarily completely replace a lot of what we do in research. So, a lot of research, clinical types of research, the gold standard would be like a randomized controlled clinical trial. Machine learning isn't really, at least in its current iteration, isn't really set up to do analyses of those types of studies. They're more of learning in practice, right? So it's more of building a model into your system that can learn iteratively with new data. And so I don't think that it'll ever completely replace the traditional methods that we use, because I think those still have their place. But I think that the machine learning techniques and the AI that we're seeing built does take advantage of the large, complex data sets that we have available to us that haven't historically been organized well so that we could take advantage of them. So, prior to the implementation of EHRs and prior to capturing a lot of robust clinical data, there wasn't really a data source for AI algorithms to work on. Now that we have these EHRs in place, there's a lot of robust clinical data that we can leverage, and I think that's where AI kind of steps in and has its place. It's how do you use this robust data that we've collected as part of the clinical care for children in the treatment of future children. Okay, so we've seen historically thousands of children with asthma come to our hospital. How can we use that historic information that we've captured on these thousands of children in the EHR to improve what we do in the future when a new child comes to us with asthma? So I think that's kind of where it has its place, but I don't think necessarily it's going to completely replace a lot of the more traditional statistical approaches that we use.
This has been fascinating. This machine learning is really interesting to me. My last question, and I'll let you get the last word. Stephen Hawking, one of the greatest minds of our time, said that AI could be the worst event in the history of our civilization. What do you think about that?
Well, I think that he was referring primarily to humans relying completely on AI and not necessarily using it as a tool for guiding their decisions. So I'd go back to my prior comments that I made, Tony, about never getting rid of the clinician's critical assessment of a child sitting in front of them, and how AI can help the clinicians reduce their cognitive load around all the clinical inputs that you need to think about and think through. But I still think at the end of the day, there has to be a clinician who uses this AI in a critical manner and assesses it. I don't think we want to get to the point where the AI is making certain diagnoses and providing treatments and things of that nature. And I think that was more of what Stephen Hawking was cautioning against. It's not a total reliance on AI, but using it in a critical manner to improve the decision making.
I agree with you 100%. Matt, this has been fascinating. This is a topic I know very little about, and I have really enjoyed this conversation and learning about it. Is there anything I didn't ask that I should have asked that you want to let us know?
Well, Tony, thanks for involving me in this. I think it's been really helpful to put my thoughts together and to share them with your audience as well around machine learning and how machine learning techniques and how they can be useful. I think we covered the vast majority of things at a high level that people need to know about machine learning. I will say that, if you go to Pediatrics, the journal, if you go to JAMA and research machine learning in pediatrics, you will find several different applications that can help you see how this is useful in practice. And so it may not be completely coherent, I'd say, to your audience at this point, but it may be helpful to go research how folks have used it in the literature to get a better understanding of what this can do for us clinically. And again, I think fundamentally it can help improve our decision making, but shouldn't be the only source of our decision making.
I think that's great. Again, thank you, Matt, for your time. I really appreciate it.
All right, now it's time for our acknowledgments. I would again like to thank our special guest for coming on the show. I would like to thank all of you for tuning in to PHM from Pittsburgh and letting us be a part of your day. I would like to thank, as always, the UPMC Children's Hospital of Pittsburgh, my division, the Paul C. Gaffney Division of Pediatric Hospital Medicine, for letting us do this. Of course, the University of Pittsburgh for their support and for the free CME credit to anyone listening. And as a reminder, the free CME credit is in the description of this episode on the podcast. Thank you, as always, to Dr. Megan Tarchichi, who helps me with everything. Hey, I hope you all have a great day, and we'll see you next time.